So there's quite a lot going on in this question. First of all, we've got a context. We've got some bacteria measured with their area at time t. So we're modelling the area of bacteria. Scientists talking about rate of increase being proportional to area. So we've got rates, so d dt. And we've got to show that his idea leads to this exponential equation. So we've got to get from rates to that equation. Later, it looks like logarithms are coming in. So logarithms are used to linearize a model, to change a curve into a straight line. So we're going to have to do some work with that later and find some values. And then even further down, we're sort of interpreting and discussing limitations. So let's take this steadily. We've got quite a few things to do, but it's also worth quite a lot of marks. So, part A, the scientist's model. So let's start from that. The scientist states that the rate of increase of area, which is d, now they're using p for area, which is unusual, but dp dt, is the rate of area, can be modelled as being proportional to, so equals k times, that's the proportional to, the area of the culture, which is p again. So dp dt equals kp. Now if you look at that, that's a differential equation. We're going to get p on the left and t on the right. So we need to divide by p, 1 over p on the left, and we keep the dp. We keep the k on the right, and we bring the dt up to join it, and we stick the integration signs in as well before anyone notices. Okay, so that's what we call separating the variables in a differential equation. We integrate both sides. 1 over p integrates to ln p. K is just a number, so that will just integrate to k times t. But we need a plus c on one side or the other. I'm putting it on the right. We're aiming for p equals, so we've got ln p, so we need to take e to the power of both sides. P on the left equals e to the kt plus c on the right. And remember how that breaks up. It's e to the kt multiplied by e to the c. And we can rebrand e to the c as a new letter, a. So p equals a multiplied by e to the kt. And that is as required. So the first part of that was taking a rate, a model, which is a differential equation, and integrating it to get that exponential equation. Okay. Now she's plotting a log graph to think about a straight line. So the next bit of work we have to do is apply logs to both sides of that equation, which is actually a curve, and just see how the algebra pans out from there. So we're going to take ln of both sides. We're going to get ln p is ln of a e to the kt. Let's keep ln p on the left, equals ln of a product breaks into ln of one thing plus ln of e to the other. And that last term there, ln of e to the power kt, ln and e are inverse functions of each other. So ln of e to the kt is just kt. Now I'm going to highlight some parts of this. The scientist is plotting a graph of ln p against t. So ln p is on her y-axis, t is on her x-axis, and this is like y equals mx plus c. So k here is going to be the gradient of her line, and ln a here is going to be the, we would call it the y-intercept or the vertical intercept of the straight line that she's plotted, because she's not plotted directly p against t, that would make a curve, an exponential curve. She's plotted ln p against t, making a straight line with gradient k and vertical intercept ln a. Let's go back to reading the story. She's got a gradient of 0.14 and a vertical intercept of 3.95. So, well, k is the gradient, so therefore k is 0.14 directly. Ln a is the vertical intercept, so ln a equals 3.95, Therefore, a is e to the power of 3.95. And on your calculator, that gives you approximately 52. And the question does say in a second, estimate two significant figures, a and k. And we've given k and a, both of them, to 2SF here. So that part of the question is done. We know some actual values. And it's probably worth summarising what they tell us about the model. So the model was P equals A e to the k t. So that's the model now with those values filled in. Okay, let's move on. Part C. Hence show the model can be written in P A B to the power t. So B is a new letter here in this function. E's gone. E to the 0.14 has gone. So let's just do the writing so we make sense of this. Copying it again, P is 52 multiplied by e to the 0.14 t. And what the question's doing is grouping e to the power of 0.14. And on your calculator, if you type in e to the power of 0.14, you should get 1.15. So this p function is the same as 52 times 1.15 to the power t. So stating to three significant figures, the value of the constant b is 1.15 to 3SF. Okay, not the most useful thing to do, but it comes into the interpretation in a second. Okay, part D. Interpret the value of the constant a. And a is this value of 52. Well, if you think about it, 52 is the value we get when t is 0. If t is 0, then p is that constant a, that 52. So this is representing the initial value of p, which is area. So therefore 52, let's check the units. P was millimeters squared. 52 millimeters squared is the initial area of bacteria. It's how much was in the dish at the beginning. The constant b, so now they want us to interpret the 1.15. Well, if you've got 1.15 to the power t, think of it like an interest rate. Okay, it would be a very good bank account because it's 15% interest, but think of it as that kind of rate. So we can see that the area increases by 15% per hour, because t is measured in hours, by 15% per hour. So 1.15 corresponds to a 15% increase per hour. E, long-term limitation. Okay, probably not hard to guess, but let's do it carefully. Part E, long-term means as time goes off to infinity. Well, 1.15 to the power infinity just gets bigger and bigger and bigger. So the model suggests that as t goes to infinity, the area goes to infinity. Okay, why is that a limitation? Well, that's unrealistic, because the area is going to be constrained by the dish they're in. They can't get any bigger than the dish that's containing them, so the area is constrained by the dish. There we go. A lot of effort, but a lot of marks.